I
No.
see a presentation, but or rather, I also see each of the slides.
Ah, yes.
So it's not presentation mode, but it's now it is.
Now it
Good.
is. Okay. Uh, Continue to share. So now I don't see all of you, but I guess that's okay. uh, let's see that I have the time. So unfortunately, our colleague Ingela Nyström fell ill, so she could not present Infravis. So I'm going to present a little bit to you uh, about Infravis because I work for Infravis, which is a infrastructure, national infrastructure for data visualization. And I think it's good that you know about it. I don't know if you are researchers, PhD students, but you should know that Infravis is something that you can make use of. And it has funding for the years, as you see below there. And what do we do actually? Well, we can help people with, or researchers with their research problems when it comes to visualization, to make the invisible visible, so to speak. And in my presentation today, I will very much focus on the fact that visualization is not only the end product, sort of the pretty picture in the paper that you make in the end to show your data, but also all along a research tool. That's how I use it. I cannot today even imagine not using visualization because that's what I do all the time. As soon as I get data, I look at the data, and I will show you why in this presentation. And Infravis, as I said, is a national infrastructure, so we are all over Sweden. And you can see the people in Uppsala. I don't know if you see my pointer because I don't see any pointer. I guess you do not. So it's Ingela, me, and Jayant is also involved, and Vasiliki and Nikita are doing different things. Uh, so I think we are much more than 50 visualization experts now, actually, because yesterday I went to our Infravis days, and there were quite many people there discussing visualization problems and how we can help you. So you can get information about events and news and about the tutorials that I give and what is happening in the community, so to speak. And you can get help with your visualization or your whatever you're doing that needs visualization, and you need to discuss how can I use visualization or how I can make a visualization in the end. So in the bottom there, you have the help desk, free of charge. You can ask anything to us. You send in a ticket. You can even send directly email to me, especially after this lecture today. But in order for us to count how many we help and so on, so it's good to make a ticket in the end. And then there's this mid-level support when you have a little bit of a bigger problem that you need to solve. And in depth, that will cost money, that might concern a bigger task that you're doing. And we are not really building systems, but we can help in that to help sort of build visualization systems, but not a system that another person or programmer could do. And we don't really deal with data, but I think today you will get a tool to do it yourself. But in some sense, we can help with that too, but we don't gather data. That's something for others to do. So that was very quickly about that. So now I will go over to the main talk. And as you see of the title, make visualizations from your science. That's what we usually do, but also make science from your visualizations. So how to improve the whole research process that you're involved in. And I wanted to talk a little bit about Python. So of course you take this course, you know why you're using Python. But the thing is, I have been using MATLAB a lot for visualization because it has become very powerful in recent years. But recently, I have also been using Python much more for visualization, especially for teaching, because you use Python and everybody does. And I wanted to emphasize these three libraries or packages that you can use for visualization. And matplotlib is very similar to what you have in MATLAB. Seaborn is used a lot in statistical visualization, but simplifies matplotlib a lot. And then Plotly for interactive visualizations. So you can use all of these three. And why not use Plotly all the time? Well, perhaps you don't want interaction, and then you should perhaps not use it. Seaborn simplifies a lot, so it hides a lot of the complicated stuff you can do in matplotlib. But sometimes you really need to specify something very special, and then you have to use matplotlib. But usually you can use it in combination with Seaborn. But Seaborn simplifies everything a lot. So my advice is to start with Seaborn and only use matplotlib when you sort of need to do something very specific. And if it's an interactive application you're doing, start with Plotly from the start. And here you have the links to these pages. And I wanted to say something important about this, because when I started as a programmer, we had these shelves, bookshelves of manuals, manuals for the compiler and for the language. And pick them
Uh,
up.
Adarsh, your voice got cut. Secondly, are you still on the first slide or have you moved forward?
I have moved forward a lot. Is there something
Oh,
wrong?
yeah, we are still seeing your first slide, unfortunately.
Oh, wow. That's crazy. So for some reason, something happened with my internet, I think, because my the AC started to started to roll without me wanting it. So if I show this slide now, what do you see?
Yeah, we see how to use and then it's cutting. It's not showing, it's not fitting the whole screen.
Aha. Why is it so? Ay, ay, ay. And do you see now? Let's see. That's strange. Okay, thank you for. There's something which is different this time. I don't know why. So now you see also the list of things in the.
Yeah.
And if I do you still see?
Yeah, this fits well.
And now it says continue to share. So I press continue to share. Still okay?
Yeah, it's still okay. I tried moving the slide
Did it
back and forth,
change?
like the next. No, it did not change.
Did it change?
No, it did not. Still
What?
on the.
Yeah. I don't know what's going on here. Now?
No.
So, okay, if I do like this, do you see it?
Yeah, we see the tools and yeah, we see the screen.
Does it change when I do like this?
Yeah, it does.
Okay. Yeah, this has never happened to me before. I don't know what's wrong. So sorry for that. I don't know if I can sort of remove this one. I don't know how to do that. Okay, but perhaps we can run like this then. Now something happened here. Okay. So what I wanted to say is that we don't have to remember everything by heart anymore, because on these pages that you have the links to, you have a lot of examples of how to use these. And when I started as a teacher, we had to make our own examples to be sure that they were always there and we had control of them. But these examples will be there and they are really good. So please have a look at these pages. You will learn a lot from them. All kinds of different visualizations. So you can use them as a base to build upon. And whenever you want to do something kind of particular, I use ChatGPT or Gemini or something to ask, how do I do this and that? And sometimes it works, usually it works, but not always, as you know. And usually you get an example which is kind of primitive, and then you have to ask for something more advanced or more compact, and you get that. So I guess most of you have tried this already and perhaps know it much more better than me, but that's how I work, and I see a lot of students work like that nowadays. So you don't have to remember everything. So now I will talk about this dimensionality reduction and what that is, and I will skip this slide. So we go directly to this thing, because I think many of you deal with machine learning in some way or another. And I want to exemplify how dimensionality reduction helps and how machine learning works a little bit. So if you were to go out in the city and ask people that you see 100 different questions about how they live their life, could you from those questions deduce if they are living in Uppsala, or rather if they are students at Uppsala University or if they are students at another university? Let's take that as an example. So there are, of course, many questions that have nothing to do with if they're students in Uppsala, right? If they have a long breakfast or if they skip breakfast or something, is perhaps not relevant. If they are connected to a nation in Uppsala, well, then that's a really, really strong evidence that they are students in Uppsala, right? Or if they are in a nation or a student union I live in Gävle, like Högskolan i Gävle. Okay, then they are not probably students in Uppsala, but they could be students in both. So all of these 100 questions gives a strong or a rather strong or a weak kind of classification if they are in Uppsala or not. So if you take all of these 100 questions and make a feature vector of them, then the machine learning tries to separate those two classes in this 100-dimension space somehow. And we can visualize it like this. Now perhaps you see my pointer when I move it around.
Yes, we can.
Yeah, you can see it. Okay, because I see it too. So if you can take this 100 dimensions down to 2 and you get a separating curve, like this green curve, then you have a perfect separation between Uppsala and non-Uppsala, let's say that. And perhaps you know that such perfect separation is called overfitting. It really fits to the data you train on, but if you add more persons, it will not fit very well. And then we use this black curve instead, because if you add 1,000 new persons, you will probably get some blue persons within this green curve that we classified as red, but those we call outliers. They are very, very special. So could be one that was born and raised in Uppsala, but and read Uppsala Tidning and whatever, but studies in Lund, for instance. That can happen. So the black curve generalizes better. So now what we want to do, we take our 100 space and project down to 2D without any machine learning. And if we get this kind of separation, even though it's kind of fuzzy, then we know that, okay, machine learning will probably be able to separate these two things as well. But if you get a complete mess of blue and red dots, from dimensionality reduction, then we have a problem, because then machine learning will probably not be able to do anything about it. So we can look at our data in advance and get some ideas about what will happen. And we might also detect outliers and perhaps errors in our input data. So that's what I want to exemplify now. So there are different dimensionality reduction techniques. I will not talk about self-organizing maps, but that's something you can look at. I will talk about PCA, TSNE, and UMAP. And perhaps you have heard about these different techniques before. And I will try to show to you what they do and how all of these three actually can be useful. But what we have to remember is that when we have a high dimensional space and we project down to a 2D space, we don't really get the true image. We get a projection, which is pretty close to the truth, but not really. So we have to be careful how we interpret things, and that's something I would like to show. Okay, principal component analysis, or PCA. Perhaps you have used that in your research. It's very popular, not the least for reducing the size of that data, noise reduction, and so on. And how does it work? Well, I understood it from computer graphics, since I come really from computer graphics field in the beginning. So if you have this dragon, for instance, so here we have only points, but for a 3D object, we also want to triangulate this point. But if you just look at the vertices, the points of this dragon, and we want to make something called a bounding box, then this bounding box is perfectly fitting this object. And it can be used because if you do ray tracing or object collision and so on, like if you shoot an arrow towards the dragon, do I hit the dragon or not? Well, if you hit the box, then you might hit the dragon. If you don't hit the box, well, then you don't hit the dragon. So this is a technique we use in computer graphics to reduce the problem. So if you take all the 3D points in the 3D world, and then you do PCA on them, what you get is these eigenvectors. The red one is the most significant one, the one that's sort of the main direction of the object. And then you get the second direction, the green one, and the third, the blue one. And actually, you can have 4-dimensional or 5-dimensional or 100-dimensional objects, and you get as many eigenvectors as you have. So how can we use this then? This is kind of how it works. Well, we can use it for dimensionality reduction on data. And if we take the iris data set as an example, perhaps you have seen that before. It is used in many situations for, yeah, like a toy example, really. But they have measured the dimensions of the sepals and the petals. I almost don't know what that is, but you see it in the image there. So if you take those 4 values and then you plot them in a parallel coordinate system, you get a plot like this. And this is what I used before I knew about dimensionality reduction techniques like TSNE and UMAP. Because if you have one flower, you can see, okay, the first measurement is up here, and then it goes down to the second measurement, third and fourth, and so on. So you can follow the different flowers in this parallel plot. And here we can see that this dimension in the measurement seems to be a very, very discriminative. You can really differ the 3 different kinds of flowers here, and also this one. But here it is a little bit more fuzzy, and also here. So you can imagine if you have several hundred dimensions that you cannot really know which dimension is important. In our Uppsala case, which question is really classifying Uppsala students from the other students, and so on. So if you don't know that, it's a problem. So we can use PCA because that sort of shifts the most important thing to the beginning. However, now it's not a question anymore, or it's not a measurement anymore. It's something which is kind of the most significant part, and the second and the third and the fourth, and you see in the end you have something which is kind of messy. So this tells us several things. One is that perhaps you can remove the fourth one, or even the third one. They are not discriminative. You can compress your data, your input data. And the second one is then that you can take those two axes and shift them like this, and you get these axes and plot those data you have in, and you get this kind of plot. And you can see in the blue ones are really kind of separated from the rest. The red and yellow are very close. So PCA tells us something important about this data, and this is often used in DNA analysis, for instance. Perhaps some of you are from that field. You know that you can take the DNA from people around the world, and you take some important parts of the DNA and do PCA on that, and you plot it, and you can see really the different parts of the world that people come from. However, it doesn't work for everything. And MNIST is a data set which is sort of a toy MNIST, or like Hello World example for machine learning. And it's all of these different kinds of handwritten numbers. And if you just take the image of those, flatten them, and make a feature vector of it, it's really a stupid thing to do, but it's a toy example. And then you do PCA on those flattened images, you get this mess. You can see that, okay, those numbers are pretty much clustered, and the red ones, blue ones, and so on, but you have an overlap. And the overlap is due to the fact that it cannot project perfectly because you have only 2 dimensions. If you had 3 dimensions, perhaps they would separate in 3D and 4D and so on. You get a better separation. But still, it gives you some idea of how it works. But then we have the magic, TSNE. When I saw it the first time, I really thought it was magic. I couldn't understand how wonderful it works. So with TSNE, just working on the flattened image, you get these things. And now you can really see that you have almost 10 clusters here now. Many are pretty well separated, others are not, because some numbers are kind of similar sometimes. 1 and 7 can, for instance, be very similar, depending on how you write them. So what is this? Well, I never remember even what it's called, because it's a little bit complicated. But this was invented by Geoffrey Hinton, who got the Nobel Prize last year, and perhaps mostly by his PhD student, actually, from the Netherlands. I have tried to understand how this works, reading the paper, reading the code. It's kind of complicated, but the idea is very simple. And that is, if 2 images or feature vectors are close in high dimensional space, they should also be close in the two-dimensional space. And if they are far away in high dimensional space, they should be moved away in two-dimensional space. So it's an iterative algorithm, and it starts by just a random guess, just plots each data point in 2D, and then it tries to move, as I said, if they're close in high dimensional space, move them closer in 2D, and vice versa. So you can really see how clusters form and separate if you visualize it iteratively. So yeah, that was a very brief explanation of a very complicated thing. But as I said, it starts with a random guess, which is kind of stupid if you think about it. Why not start let's see if I can go back now. Oops, what did I do? There, no, there. why not start with PCA instead? Because then you have a really good start. You will iterate less because clusters are already formed. You just have to move them apart, kind of, and compress them. So that's one trick I want you to remember. Use PCA as a start. And then we have UMAP, which works in a similar way. The idea is kind of similar, but the mechanics behind it is different. Yeah, you should read the paper. It's interesting to look at it. And most PhD students use this, and even researchers, because there are many papers that tell that UMAP is better. In the exercise that you will do on your own, you can see that perhaps it's not always better. But in the image, you can see that it separates clusters better, and it moves them, it compacts them, and it moves them further away. But one disadvantage is then, if one cluster is very unusual, it's not like any of the others, then you will have a big separation. So you will have a lot of empty space between these clusters, while TSNE tries to form a cloud always. So that's one important difference. Another one is that UMAP doesn't always allow you to use PCA as a first start. And I honestly don't know why, but I got, at least in MATLAB, I get some like the rank of the matrix or something. You cannot use that matrix, and it fails. I haven't tried it in Python, so I let you do it and see what you get. So let's see. So now I want to show you some examples from projects I've been working with, and where I have learned a lot about these methods, and really gave me inspiration to keep using these methods. And I should say that always try PCA, TSNE, and UMAP and see what works best for you, because it might be one of those. So don't get stuck in one of them. Anyhow, City Faces is a project that ended. They have an exhibition at the City Museum now in Stockholm, so I recommend you to go and visit. It's a small exhibition, but it's kind of nice. And it actually got, I saw today, I should say, won the prize for best exhibition in museums or something like that. I need to check this further because I just saw it on LinkedIn. So it's kind of cool. But here we looked at people living in Stockholm 150 years ago and tried to connect them to archives and different photo collections. The second project, which is still ongoing, is EB Crime, where we try to figure out the age of people using their face only. And I shall show you some interesting results from that. So face recognition is perhaps nothing you have tried, but there are packages you can download and try. And if you really want to do it, I recommend you to do it because it's kind of fun. I didn't want to do face recognition really because I sort of connected it with surveillance and these things, but there's so many things you can do with it. Emotion detection for Alzheimer patients, for instance, is something I would like to do. Yeah, this City Faces project was a lot of fun. So first thing is to detect faces. The second thing is to align the face, sort of straighten it up and cut out the face, and then get the feature vector out of it. So the nice thing is that the pipeline we're using, it doesn't have to see your face ever before. It hasn't trained on your face, but it has been trained on how to recognize any face and describe it in a good way. So you can put in any face and you will get a feature vector. The problem is that if you come from a part of the world where little data has been trained on, or if you're in an age span where they have used a little data, then it will work a little bit less accurately. So it's a little bit biased always, but they try to remove the bias as much as they can. And I used something called DeepFace, and you can check it out. It has different algorithms for this detection and alignment and making feature vectors, and you can design your own pipeline using your favorite methods. And I was really happy with DeepFace. I got really good results when I was trying to search for people in different data sets. And since I'm doing visualization, I of course wanted to know how does this cluster when I have this is actually from the police register. So these are thieves and other people that got caught by the police at least 150 years ago, something like that. And then I got a kind of a cloud here and a long tail. And this told me this cannot be right. There's something wrong here because TSNE doesn't make a tail really unless there's something really strange. And if you look at the people here, perhaps you can see that they are all profile faces taken from the side because it's from the police register. They wanted the profile and the front face. So, and it doesn't matter really what person it is. All persons down here are profile faces. So this told me something very important, that the pipeline could not produce a correct feature vector from the profile faces. So perhaps the alignment, or rather the training of it hadn't been adequate for profile faces really. So then I had to change, and I changed to insight face, which is really easy to use, and you can download that too online. And now you can see you get small clusters of each person here everywhere. And if you zoom in, you can see here we have one person, you have profile faces and almost front faces and so on. Same for this person and so on. And interestingly, they all have a mustache and look kind of similar, but they are different people and they are clustered, so TSNE can handle them. So it just works on the feature vectors, and you get this nice clustering. And now it tells me, okay, it works for both profile and front face. And something which is you can try in the files you will get is to make a convex hull for each cluster. And this is something I learned on the conference. And it's really interesting because now it really sticks out where the convex hull is kind of strange. Like here, you have a elongated. So this person here, is it really the same as that person? Is there something wrong in the data? It could be. Or is it so that there's a huge age gap between the photographs? Well, then you can have this behavior. And in this case, you have something on one side and something on the other side. It could be the same errors, but it can also be that it's actually the same person. And why? Well, you can think about this cloud more like a cylinder, it seems like. That's my interpretation, at least, that sometimes it happens that the same person ends up in two different places for different reasons. So something which is here is actually close to something which is there. So we cannot trust the distance in a TSNE or UMAP plot. You cannot trust them always. So be careful there with the interpretation. It's good to be aware of those things. And I should tell you a little bit of some examples. I was approached by TV a couple of years ago. Perhaps you remember this. There was a woman that appeared together with Putin in many different occasions, and there was this rumor it was an actor. And TV asked me, is it the same person or not? And I thought, okay, it's the same person. They look the same. They have the same haircut, blonde, and so on. And I tried it, and what happened? Well, you can compute the cosine similarity between two feature vectors. So you will get a value between -1 and 1, and if it's close to 1, it's probably the same person. If it's closer to 0, it's not the same person. But I ran TSNE anyway, and what happens is that you get two clusterings, and they are close, which is kind of interesting. But if you compute the similarity between this woman in all of the different settings, you have a very high similarity. But this woman has a higher similarity because it's from the same photo occasion. So there's no time change and no lighting change and so on. But the similarity between those two groups is very low. And that told me, okay, they cannot be the same person. And that was surprising for me. But when you look closer, you could see that there is actually an age difference between those two women. And interestingly, this blonde woman is more similar to this dark-haired stewardess that were in another occasion. So we wouldn't say that these two are equal because they look so differently. But the geometry of the face is more similar between those two than those two. So this tells you a little bit about how important it is not to be fooled by outer appearance, but actually look at what the feature is made from in the end. So yeah, the similarity here is very low, but there is some distance which is close anyway. But remember this: if you look at the Orion belt, they seem to be very, very close, right? But if you look in space, they are actually very, very far from each other. So that's what happened. We project from high dimensions down to 2 dimensions, and we lose something from it. Okay, another thing I worked with was sex estimation, or some would call it gender. I use the word sex just because that's what my forensics colleagues use when they work with skulls. They try to figure out was that when a woman or a man. And in this case, I saw one beautiful man and 2 beautiful women, but it was not. And this is in the 1870s or something. So it's a long, long time ago. And what happened was that I took the feature vectors, I ran TSNE, and since I had the gender or sex from these people, I plotted a red dot for women and a blue dot for men, just to make life simple. And one interesting observation is that all women kind of ended up here and all men ended up there. And this is not so surprising because our geometry, our main geometry, so to speak, differ because we usually can differ between a man and a woman. And I was fooled by this man because he ended up there, kind of close to the women, but still there was some space here. And remember what I said, being close to the edge might mean that you're close to an edge somewhere else. And there were blue dots, and I thought, okay, this person has been wrongly annotated in the data. And I looked in the data and it said, no, it's a man, Carl August Lundström. He was caught by the police as a ladies imitator. And he did some other stuff, stealing and so on. So that was an interesting surprise, but it also made it possible for me to make a very accurate estimator for if it's a man or a woman. Using feature vectors. I didn't have to train at all, but that's another story. Okay, aging is something we are all suffering from, unfortunately. And what happens when we age? I tried to figure that out, and I have a very clever master thesis student who made a model training on faces, and he got this result. And this is interesting, and I recommend you to do the same thing if you can, because if you have a model that you have trained, instead of doing the classification as you have here, you have different decades. So these are the decision boundaries. So if you're between, I don't know, 20 to 29, I think it's there in the yellow area. That's right, yeah, the 20s and the 30s and so on. So instead of making the classification, you take the second last layer and treat that as a feature vector. You can extract what that layer produce. It's not the weights, it's what it produces, and you get a feature vector. And if you take it, or you feed your network with all the persons or whatever data you have, and you extract this feature vector and run TSNE on it, or UMAP or PCA. In this case, it's TSNE. And I got this result. And I was super amazed because it wasn't a cloud. Two kind of beautiful snakes that are connected in the beginning and the end. And not surprisingly, it's men and women. And the network was never told who was a man or a woman, but it figures this out itself, because it has to sort of separate this in some space, because we look differently and we age differently, and we look different in different ages and so on. So it has to treat it differently. And then I took another data set, because in TSNE, it became more like two cloud-like snakes. It was more beautiful using UMAP, but we have another strange thing in UMAP. You can see that they are kind of intertwined in UMAP. And I thought first that, okay, we look the same in this age, men and women, but it's not that, because it was not the case in TSNE. So it's more like you have two snakes that are intertwined and UMAP are not able to separate them. So if we had 3D, they would be separated. So this is little a disadvantage with UMAP, that it couldn't do it. But the plots were more beautiful. So once again, try both to compare. And again, we had this case of man and woman. And remember this, we are in 3D or high dimensional spaces, actually 512 dimensions, and you try to plot them down to 2, and it's not always successful. So in the end here, what have we learned? Well, I always use PCA as a first start guess instead of randomness, because you get more the same result. But you must be careful. In Python, there's also another random parameter, because in the iterative process, it does something stochastic, as I understand it, which is not really done in MATLAB, or perhaps it has set some random variable permanently, like yeah, you usually set the first seed to 42 or something. So it's there. And now I haven't showed you so many cases, but TSNE usually works better for me in what I do, but it might not be for you. So please try both of them. So I think I've said this already, and you're always welcome to email me in questions that you might have. And yes, I have one final remark here. And sometimes you don't have really a feature vector or something, but you have, for instance, a confusion matrix or a similarity matrix of what you have done. And the nice thing, at sometimes you can use that matrix and take the rows or the columns and treat them as feature vectors and run TSNE on them, and you will get something. If your confusion matrix is very fussy and chaotic, it might not work. But if you have clusters, because usually you make a confusion matrix to show where it works and where it not works, and where it works, it will actually cluster, and you will see those that are more similar to others. So that was my final conclusion there. Thank you for listening.
Thank you so much, Anders. So this brings us to the conclusion of 4-day workshop HPC Python. And I would request people to fill in the evaluation form, and I'm sharing the link in the chat. Please tell us how you felt about this whole 4-day workshop, about each individual day, and how was your input. And you're free to leave after that. I'm keeping this session up for another 15 minutes. That is until 4 p.m. If anyone has any questions for me, for Anders, or any one of us, please feel free to ask.
Yeah, please, if you have questions about any of what I've told or about Infravis or Python for doing these things, I'm happy to answer. And sorry for the confusion in the end. That was very surprising, but that's technology. Never works as intended.
I can also add that if people want to like test out an example of dimensionality reduction, it's in the session, like the documentation. There's a like in the end, there's an exercise that Anders has prepared. So it's a Jupyter notebook one can run, and it's provided in the exercise folder itself for day 4.
Very good you mentioned that, Giant, because I made those exercises some year ago, and I didn't update them, and that's by purpose, because I use a little bit older ways of doing things, and with the Plotly and Seaborn, there are better ways to do them. So I think it's a really good exercise to try to improve it and make it more efficient. I've done that myself as well, just to learn. So usually you can do a lot in Matplotlib, but then go on to the other and do
I
it.
see this one is for face recognition. It requires Matplotlib,
Yes.
Plotly,
Yes,
and
and hopefully it will tell you all a little bit why I prefer TSNE than UMAP. But sometimes UMAP is better. I must say that. So. Any questions? Otherwise, I will go and drink some water. I was walking for an hour to get here from the train, very fast.
Thank you so much, Anders.
Yeah.
You can drink some water now. And I
Yeah.
think the learners are trying to fill in the evaluation form right now.
Okay, thank you. Yeah, and I wish you all a good weekend. Bye-bye.
Bye.
Yeah. Thank you. The same.